hopefully I can get through. All right. Maybe a better marker. So, first we make this observation. If I take my matrices for my QR factorization, U1, U2, and R1, R2, and I go ahead and work out what they are. So, whoops, that's R2, R1. Now, U2, R2, I have from over there. That is H1 minus mu1 identity, and then I still have R1. So then I can go ahead and distribute
should it be H1 minus mu2?
Yes. I should look at my notes more often. Okay. Now, U1, R1, I can express as a QR factorization from over there also. And H1, I can express as R1, U1 plus mu1 identity. I still have that. Minus mu2, U1, R1 is equal to H minus mu1 identity. Now if I multiply this out, I get U1, R1, U1, R1, so that's squared, plus U1, U1, R1, minus all this still. Okay. U1, R1 squared, that's H minus mu1 identity squared. And then the same thing over here. Okay. So now what I can do, I can expand all of this, and I'll cut to the end. It's H squared minus mu1 plus mu2H plus mu1, mu2 times identity. Now, here's the thing though, mu1 and mu2 are complex. However, if we're dealing with a real matrix, these are complex conjugate pairs. So u1 is A plus bi, u2 is A minus bi. So what that means is mu1 plus mu2 is 2a, the imaginary parts cancel out, and mu1 times mu2 is a squared plus b squared. So it turns out that even though u1, u2, r1, r2 can be complex, if I multiply them all together, it's a real matrix, because H is real. Furthermore, if I group these a little differently, this is orthogonal. This is triangular. So what I have here is the QR factorization of a real matrix. And I can go ahead and form this matrix. So I'm going to call this matrix M. So it's a real, so no matter what the eigenvalues are, M is real, and I have some, I know something about its QR factorization. Okay. Another observation I can make that actually follows directly from what I wrote down earlier. All of this tells me that H2, my output matrix, is a pair of similarity transformations applied to H. Because this applies one similarity transformation, this applies another. First with U1, then with U2. So, and I can group these together. That's U1, U2 transpose H, U1, U2. So this gives me another way to proceed using only real arithmetic. So I'll describe that very quickly. This is called the double implicit shifts strategy. So I'm going to implicitly use these two shifts without performing any complex arithmetic. What I do is I go ahead and form this matrix M that I wrote down earlier. I go ahead and compute these eigenvalues, but I'm only using real expressions. Okay. Next, I go ahead and QR factorize it. So I compute z times r. Z is orthogonal, r is over triangular. So z is u1, u2, and r is equal to r2, r1. But I'm not actually computing those. But it's relating to what I had earlier. And then I get my matrix, my output matrix H2 is Z transpose HC. So now I'm able to avoid complex arithmetic. So you might think, okay, now I'm done. Well, I'm done with class. But no, we're not done, because this is a matrix multiplication as order n cubed plus. And we're trying to keep our process per iteration at order n squared. We just violated that. So no, we cannot explicitly form now. So much for that. So this problem will be resolved with the A to B implicit Q theorem on Monday.